Assalamualaikum students. Students, in this lecture we are going to do sigma bonding, pi bonding and hybridization, right? Now, what is sigma bonding? The bond that is formed by the head-on, axial, head-on or axial overlap of two half-filled orbitals. The shared pair of electron is always between the two nuclei. The experience more nuclear attraction and free rotation around sigma is possible. Look, if I explain this in a very simple way, it would be like this, that for example, there is this s orbital. You know, s is spherical. It's like a spherical, three-dimensional nucleus. There is another s orbital, like hydrogen. This is hydrogen, it is 1s1. This is another hydrogen, which is also 1s1. If these two hydrogen atoms, if their s orbital, they get close, they will overlap? Yes. When they overlap, what will happen? Look, if I bring them close, what I'm going to do, wait a minute. Like this is one, and this is the other that is coming closer. So they are overlapping. So this is the shared area. The electron cloud are between the two nuclei. The two electrons are between the two nuclei. They experience more nuclear attraction. We usually represent this by this. Like the two hydrogen, their s orbitals overlap, and these are the nuclei, and this is the electron cloud is between this area, right? Between the two nuclei. Now, if suppose now one is p orbital, for example, one is p orbital. This is a p orbital. This is an s orbital. S is spherical. P is dumbbell. They're coming closer. They're coming closer. They will overlap like this. Look. They will overlap like this. Look, when they overlap, one thing, the electron cloud, the shared pair is between the two nuclei. The electron cloud is between the nuclei. The electron cloud is at this place. There is very low probability that the electron will go to this side. So what you are supposed to do? You will shorten. Like this side is shortened. Why? Because the electrons are between the two nuclei. They are negative, they are positive, the electrons are inside, they're not moving to the other side. So how we usually represent it? Like this. This is nuclei of the S side. This side is short. Like it looks like a fish, if I'm not wrong. like this. This is this nucleus. So the electron cloud is where? At this place. The probability to go to this side beyond this nuclei, very, very low, kind of impossible. Now, if the p orbital is this way, like it's py, and there is this s and they're coming closer, so if they're coming closer and they're going to make a bond, so how you will show this bond? It's like this, look, it's like this. This is the nucleus, and this. Huh? But if there are two p orbitals, this is one p orbital, this is another p orbital, this is p1, this is also p1 half-filled orbitals, then they are coming closer, they are going to make a bond. So what will happen? Like this, the other is like this. The shared pair is between the two nuclei. This is the region where the probability of electron is very large. This is between the two nuclei. So the electron are not going to this side, not going to this side. So what we are supposed to do? Shorten this side. Because this is not the region where the electron would go. So how we are going to represent it? This is nucleus. This is the place where there is probability of electron. And since, look, this is head on. This is also head on, axial. So when there is axial overlap of two half-filled orbital, what is formed? Sigma bond. I agree that when I will be teaching hybridization, you will come to know that it's no longer the P and the S, it's actually the hybridized orbitals. Hybridized orbital that actually make sigma bonds. This I'm going to explain after pi, right? Now, what is pi bond? You know what is pi bond? Pi bond. The bond that is formed by the sideways overlap of two half-filled parallel p orbitals. The electron cloud of pi bond is above and below the bond axis, experiencing less nuclear attraction. Therefore, pi bond is weaker than sigma bond. The pi bond is weaker than sigma bond. And free rotation around pi is not possible. It breaks the pi. It breaks the pi bond. Now, look. This is one p orbital. the nucleus. This is another p orbital. They are so close. They are brought closer by sigma bond. Keep in mind, single bond is always sigma. Double is sigma and pi. Triple is sigma pi and pi. This shows that pi alone is not possible. The sigma bond, the sigma bond, this is sigma. It brings the parallel p orbital close enough this way. Look. So this is the shared region. And this is the shared region. The shared region, these are two nuclei. Look, these are two nuclei. Now, this is sigma bond. This is sigma, and this is one pi bond. So, how we represented this is nuclei, cloud above and cloud below. Like we simply represented by this. Like this is the cloud above, the cloud below. Now listen. I'm going to relate this with the hybridization, the sigma and the pi. But before going to this pi bond, the bond that is formed by the sideways overlap of 2p orbital. When they are brought closer, they overlap above and below. In 2p orbitals, look, this is one p orbital, this is another p orbital. They are brought closer. There is the sigma bond. They overlap above and below. They make what? Pi bond. And it is exactly this thing, right? And this is the representation. Now, if you will rotate it, it will break, right? Like you can't rotate around this bond. The pi will break. And second, the shared pair is above and below. Is this far from the nucleus? Like when you compare the sigma and the pi, the sigma electron are between the two nuclei, but the pi electron are above and below. They are far, they experience less nuclear attraction. So it's a bit weaker. Now your next topic is what? Hybridization. You know what is hybridization? Mixing of different orbitals to make equivalent orbitals. sp3 hybridization. What is the meaning of this? I'm going to explain this, but first let me to write the some required material. sp3, mixing of 1s, that is not this 1s, it's actually ONE, mixing of 1s, because when you say 1s, like it is s of first quantum shell, and I'm just saying any 1s, right? Mixing of 1s and 3p orbitals to make 4 equivalent orbitals. sp2 mixing of 1s and 2p orbitals to make 3 equivalent orbitals. sp mixing of 1s and 1p orbital to make 2 equivalent orbitals. Now, first, the angle associated with sp3 is what? 109.5. This is 120. This is 180. Right? Now, let me explain this whole thing. Then what is hybridization actually? Look, I'm starting with water. Then I'll go to carbon. With water. This is H2O. This is H2O. Right? This is water. Now, if I take oxygen, it is what? 8. In oxygen, this is 1s, then this is 2s, and this is what? 2p. This is 1s2. This is 2s2. This is 2p4. Now listen. This is 1s, 2s2, 2p4. Look, when we draw this dotted cross, actually 1, 2, 3, 4, 5, 6 is going to make 2 bonds. Yes. Now, when you do this in your mind, you think that they're exactly at the same distance from the nucleus, and they are. Like, since O levels, when we draw this dotted cross, we think that they're in the same shell, in the last shell, there's 6 electrons. But if I look at this configuration, if suppose this is the nucleus, look, this is the nucleus. Now look at this. Is the 2s and this, are they exactly at the same distance? Like they are in the second shell. This is the second shell. Look, 2 and 2. But do you think that this pair and this pair, are they exactly at the same distance from the nucleus? No. Like if I look at this thing, you will find that this pair is closer to the nucleus and this pair is far, which is not the case actually. But if I look at this configuration, it seems to be like this. But if I look at this one, they're exactly at the same distance. You know what is the real situation? They are exactly at the same distance. But how? You know what happened? Actually, when this oxygen will do bonding, it will mix the S, the 3p together. So it's mixing of the S and the 3p. After mixing, equivalent orbitals, four are formed. Why? How many orbitals are mixed? One orbital, two orbital, three orbital, four orbital. They mix. They make new four orbitals and they are called what? sp3. Why? Because it is made by mixing of one s. And how many p? After mixing, they are called what? sp3, 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 sp3. There are how many electrons? 1, 2, 3, 4, 5, 6. So if I put these 1, 2, 3, 4, 5, 6. Huh? So now in oxygen there is one sp3, another sp3, another sp3, and another sp3. sp3, sp3 orbitals. When you say that hybridization is sp3, sp2, you are actually trying to say that the orbitals are now sp3. In these orbitals, there are these two electron pairs, and there is this just one electron. So the hydrogen will come, and the hydrogen, the S, the sp3, they are overlapping. This is head-on overlap. This is also what? Head-on overlap. Huh? So this sigma bond is made by which overlap? This sigma bond is made by sp3 and s overlap. Do you understand? Huh? Like in water, the oxygen is not having the p and the s orbital that are making the bond. You know, these bonds are not made by the p, they are made by the oxygen is what? sp3 hybridized. The oxygen is what? sp3 hybridized. So this sigma, the single bond is always sigma. This sigma bond is made by sp3 overlap. The same is for this too, right? And these pairs are present in sp3 orbitals. Now, before further explanation, how to find the hybridization of an atom in a molecule. What you are supposed to do, you will count the electron region around that atom. Count electron region. You know what is electron region? The electron region is single bond, double bond, triple bond, lone pair. Each is one electron region. Count electron region around each atom. If there are 4 electron regions, it is sp3 hybridized. Means its orbitals are called sp3 orbitals. If there are 3 electron regions, sp2 hybridized. If there are 2 electron regions, sp. Now we are going to apply it. For example, CH3, C double bond O, OH, for example. Now, first, look, you can't ignore, you can't ignore group numbers. Keep in mind. The group number of the carbon is what? 4. 4. So 1 region, 2 region, 3 region, 4 region. There are 4 regions. It is sp3 hybridized. Now, this is single bond. This single bond is sigma bond. It's made by what? If you say it is sp3 hybridized, you are actually trying to say that its orbitals are sp3. So this sigma is made by the sp3 head-on overlap. Overlap. Spelling is. So this sigma is what? sp3, sp3, sp3. What about this? But wait, let me draw parallel to this. The carbon is what? One sp3, another sp3, another sp3, another sp3. So this is what? Hydrogen is what? 1s1. This is sp3 overlap. sp3, sp3 overlap. What about this carbon? Carbon group 4. 1, 2, 3, 4. No lone pair. 3 regions. How 3 regions? 1 region, 2 region, and 3 regions. So what is the hybridization? sp2. So this carbon, sp2 1, sp2 2, sp2. sp2 are 3. Look, mixing of. Where have I written? Mixing of 1s and 2p to make 3. So if there are sp3, they would be 4. If there are sp2, they would be 3. If there are sp, they would be 2. So sp, the last one is not equal in size. Try to make them equal, but I agree my drawings are not good. So this is what? sp2, sp2. So this sigma is made by what? sp2 and sp3 overlap this sigma, right? This is what? sp3 and sp2 head-on overlap this sigma, right? What about the oxygen? Oxygen of group 6. 1, 2, 3, 4, 5, 6. So if this is 6, how many regions? 1 region, 2 region, 3 region? sp2. So this oxygen, sp2, one pair in sp2, another pair in sp2. This is also sp2, and this one is also sp2. So this sigma is due to sp2, sp2 overlap, right? And at the end, we will talk about this pi bond. I know this is sigma and this is pi. I'm not going toward the pi right now. At the end, I will talk about the pi. Now look at this oxygen. Group 6. 1, 2, 3, 4, 5, 6. So how many regions? 1 region, 2 region, 3 region, 4 region. This is 4 region. So hybridization is what? Hybridization is sp3. So this oxygen, coming to this oxygen, this is what I want to draw this green. This is sp2, no, sorry, sp3, 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 and sp3. Agree? Right. This is a pair in sp3. This is sp3 with sp2's overlap sigma. This is also a pair in sp3. And this sp3 is sigma bond with the hydrogen sp3. This sigma is due to what? sp3 and s overlap. Right? Now coming to the pi bond. There is this p orbital. I want. This is perpendicular to the plane of the three. This is p orbit. They are parallel. This is sigma bond. This bring the two so close that they overlap above and below. They overlap above and below and they make a pi bond. Right? Now, if you want to understand this in another way, I'm going to explain it again. But I think you understand that how you can find the hybridization of each. And then you know that if it is sp3, this is sp2, this is sigma made by this overlap, this is sigma made by sp2 overlap, this is sigma made by sp2 and sp3 overlap, this is sp3 and h overlap, right? Now, another example. Look. For example, I'm going to carbon. This is carbon 6, right? This is the energy profile. This is 1s2, this is 2s2, and this is 2p. You know what happens? The electron move to this. Agree? Yes. But even when the electron move to the high energy orbit, like if I draw this again, after moving, the electron is, wait. It's now there. When the electron move, when the electron move there, it can make 4 bonds. Agree? It can make 4 bonds. But do you think the bonds are exactly the same distance from the nucleus? No. Hybridization. Try to explain that why the element behave in this way. Like if I look at carbon in this form, carbon should make 1 covalent, 1 covalent, and 1 dative. Have you ever seen carbon making 2 covalent and 1 dative? Not at all. Never. Carbon always make 4 equal bonds. How? Even if the electron go to this, do you think it's still making 4 equal or 3 are equivalent? 1 would be smaller, closer to the nucleus. But in carbon, it's not the case. They're all equivalent. How? You know what happened? They all mix together. After mixing of 1s and 3p, so it's what? 4sp3. 4sp3. So now the carbon in this form, 1sp3, 2sp3, 3sp3, and 4sp3. Oh, sorry. 4sp3. Now it can make 4. This is what? sp3, sp3, sp3. Now it can make 4 equivalent bonds. Even with hydrogen, with any other thing, suppose it's hydrogen. In hydrogen, it would be what? In hydrogen, it would be like this, like this. This is what? sp3 overlap. This is S1. So if it is CH4, the sigma bond is what? sp3 with S overlap. Now, if carbon is going to make double bond, what is happening? I am copying this. Look, this is carbon after excitation of the electron, after excitation. After excitation, when the electron moved to this, what happened? Mixing of 2p and 1s. So what is formed? 3sp2 planars, just like the fan. Like if you look at the fan in your room, there are 4 wings and they are at 120 like Mercedes sign, right? If you look at the Mercedes sign, they're what? Trigonal planar, like this. No, it's not that. Like this, trigonal planar. Now, these 3 will make sigma bond, but this one that is left unhybridized. Is it far from the nucleus? Of course, hybridized. If it is far, it's going to make stronger or weaker bond? Weaker. Far from the nucleus, weak bond. And what is that weak bond? You know? It's going to make weak bond, and that is what? Pi bond. So, you know what happens? These 3 are like this. This is sp2, another sp2, another sp2. These are all sp2 having 1 electron in each. Now, I want to draw this again. I don't like it. Give me some time. Sorry. This is 1, another. It's like this. Huh? And they're planar at 120 degrees. And you know, this is p orbital unhybridized. Look, this is sp2, 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 and this one is what? Unhybridized p orbital. This is 1 carbon. If there are 2 such carbons, come. If there are 2 such carbons, they are like this. Oh, you know what I'm doing? It's like this. So I rotated this whole. Now they are opposites, therefore I'm erasing. These are 2 carbons. They are coming closer. They are coming closer. So what they will do? Are they going to make coming in front of each other head on? So they're going to make which bonds? Sigma bond. They're going to make sigma bond. So they're coming closer, and now I'm bringing them very close to each other like this. Wait a minute. Give me some time. They come like this, right? Like this. So they are going to make which bond? This is sigma bond, which is made by the overlap of sp2 with sp2, right? And if this is the hydrogen overlapping what? S with sp2, S with sp2 head on, another hydrogen, another hydrogen, another hydrogen. So this is hydrogen sigma, hydrogen sigma, hydrogen sigma. Now, you know what happens? They overlap sideways, making pi bond, making pi bond. Look. So, carbon, carbon. This is sigma bond. This is sigma bond. Sigma bond. Sigma. Single is always sigma. You know this. This is sigma. And this is cloud for pi. This is one pi bond. This sigma is due to sp2 and s overlap. This sigma is due to sp2 and sp2 overlap, and this pi is due to p and p overlap. Huh? Look, now if I consider the example of, suppose, I'm just giving you further two examples and then I'm going to, I think, finish this topic. If I go for triple bond, so what will happen? After electron excitation, what happens when the carbon make triple bond? Mixing of one s and one p. When they mix, there are two orbitals, sp, sp. These two left unhybridized. Huh? So, with each carbon, there is this one sp, there is this the other sp. sp and sp, one electron, one electron. One is unhybridized this, and the other unhybridized is this. This is P, and this is also P. Now, there are two such carbons like this, for example. One carbon, this is another carbon, right? They're coming closer. When they are coming closer, what they are going to do? See? This is one carbon. This is the other carbon coming closer and closer. They make what? Pi bond, sigma bond. This is what? This is the sigma bond between the two because of sp and sp overlap. This is what? S with, this is S1, the hydrogen. Huh? Now, you know what happens? These overlap with each other, making one pi bond. And these overlap, making another pi bond. So it's a triple bond. It's a triple bond. So if this is one carbon, this is another carbon, this is sigma bond. This is another sigma bond with a hydrogen. This is one pi bond and I'm showing the other with the dotted, another pi bond. But you know, the sigma is in the center, one pi bond is above and below, one pi bond is in front and at the back, like they're not exactly at one place. Like in the center, above and below, and front and back. Like मैं कहना चाहती हूँ कि बीच में, ऊपर नीचे और आगे पीछे. Like they're not at one place. क्या चीज? बीच में, ऊपर नीचे और आगे पीछे. So they're in this way, like cylindrical form. Now, not last, yes, I have to do one other thing at the end. Like suppose this is nitrogen. Like this is your question in the past paper, in the recent paper for 3 marks, that describe the bonding in the nitrogen. Now, in nitrogen, there is a triple bond, we know this. It is of group 5. So, one region and two region. Triple bond is one region and two region. Two regions. What is the hybridization? SP. What is the hybridization? SP. So the sigma bond is made by what? In nitrogen, each in nitrogen, each nitrogen atom is sp hybridized. Agree? The sigma bond is made by head-on overlap of two sp orbitals and the two pi bonds are made by the sideways overlap of two parallel p orbitals. Right? This is a description for 3 marks. Like to show that what is the hybridization? You know, it's of group 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So two regions, SP. And then sigma is made by the SP and pi is made by what? The sideways overlap of parallel p orbit. Now last, when the Cambridge or any system will ask you to draw the sigma bonds, right? So draw the sigma or pi bond. Now, first identify the hybridization. याद रखना है आपने. Identify hybridization. For example, if S1 overlap with S1, this is always sigma. This is your S. And when they overlap, they make what? This, right? Now, if any sp3, sp2, sp overlap with sp3, sp2, sp, they will make sigma bond. But how you will draw it? This is your one, like you are going to represent this by this. No difference, no worries. The other also exactly by the same. And when they overlap, what is formed? This, right? Look, when S with S, like in hydrogen, when they ask you draw H2, so what is H2? This is S, and you are supposed to show this by this one. Now, when sp3 or sp2, like this with this or this with anyone, you will draw this. Now, next, if it is S with sp3, sp2, sp, again sigma bond, how to represent? It is this, and this one is again by the same, and you will make it is the S side, and it is what? The this side. Hmm? This is the S side, right? Now, if there is a P overlapping with a P, definitely it is pi bond sideways overlap. Huh? So, how you are going to represent? This is one P, this is another P, and this is your pi. Your pi bond. Now, suppose this is your molecule. For example, this is double bond, this is N. Suppose like this, for example. Now, what is its hybridization? sp3. What is its hybridization? sp2. Nitrogen group 5. 1, 2, 3, 4, 5. So 1 region, 2 region, 3 region, 4 region. sp3. What about oxygen? Group 6. 1, 2, 3, 4, 5, 6, 3 region. sp2. Now, if they ask you to draw this bond, so which one you are supposed to draw? This one is what? sp3 with S. So, is it this one? S with sp3. So, how you will draw this one? This way. What about this one? sp2 with sp3. sp2 with sp3. This. What about this one? This sigma. sp2 with sp2. sp2 with sp2 exactly the same. This is what? sp2 with sp3. sp2 with sp3 exactly the same. This is what? sp3 with S. This one. So, and the pi is by this. Like, they will ask you to draw this sigma, this sigma, this sigma, this sigma. So, if your sigma is from S and S this way, if your sigma is from this and this way, if your sigma is from this and this way, pi is this way. I hope you understand. Now you're supposed to do the practice from the questions of the past papers, and I'm 100% sure that you will be able to understand this topic fully. And these notes would be available on my website, Chemistry by Zeenat. You must like, subscribe, and share my channel. Okay, see you. Allah Hafiz.